Good afternoon, everyone. My name is João Alves. I'm a PhD student from Nova University, and although I'm not presenting a work related with my thesis, this was a research that we've been doing after I finished my master's, and well, I'm going to present it to you. So a brief introduction about how I structured the presentation. First, the typical introduction, the objectives of the work, how we proceed to do the research, the experimental and simulation proceedings. Then I'm going to present the results and discuss them, and obviously conclude the work. So a brief introduction. As everyone here is familiar, fatigue is a phenomenon composed by 4 phases, at least according to Aston, and our research focused mainly on microscopic growth. One of the main contributions of microcrack growth was done by Kitagawa and Takahashi, which proposed this diagram where they found the pivot points where the fatigue limit didn't change independently of the defect size. Later, El-Haddad proposed a new equation which could describe the proposal of Kitagawa, but a problem still remained, since in most case scenarios, the cracks grow from defects, and which according to their characteristics, they can change the final fatigue behavior. And therefore, Murakami proposed a new model based on the hardness, the stress ratio, and the area instead of just the size of the defect. But the most important was considering the localization of the defect, since it has different influences. And this work was so interesting and so important that many authors developed different models to describe different metals. For instance, Bates et al. Developed models to describe the high cycle fatigue of a steel. Pereira et al. Used El-Haddad model, but take in consideration the Murakami nomenclature. When Tajiri and Morgado et al. Developed different equations for different aluminum alloys for different counting methodologies of the defects, and Alves et al. Developed a model for a different counting methodology. In this time, it was nanothermography, and it was to describe the fatigue behavior of a Te6Al4V alloy manufactured by selective laser melting. But again, something was missing. Those equations were good to describe the fatigue limit, although they couldn't associate the fatigue, the defect size with the SCN curve, and therefore Murakami pushed again the knowledge and proposed this equation with universal constants, which is C, M, and N, and it can describe and link the fatigue size, the defect size with the whole SCN curve. However, when testing this model using nanothermography as defect acquisition, the results were not perfect, and therefore a new proposal was made for a C and M fitted to the material itself. In this case, this titanium alloy, and it was used 3 different optimization algorithms to see if any one of them could increase the results or not. So basically, the objective of this work is to propose a new model based on the optimization algorithm to fit these parameters into the experimental data of the fatigue analysis of a Te6Al4V manufactured by selective laser melting. This is the proposed methodology. Well, it starts with getting the fatigue data. It starts with getting the defect size for nanothermography. Then we must acquire the fatigue experimental data, develop the predictive model, since Murakami used the fatigue limit of the previous model to insert them in this equation, which is represented here. Then we had to integrate the equation to use it and obtain a final area of defect and initial area of defect. And according to his proposal, the final admissible defect could be used as 1,000 or 2,000 microns. We tested both. We used the algorithms Nelder-Mead and SLSQP, and we developed the model. So selective laser melting, as I've mentioned, those were the parameters that we used. This is the powder composition and powder size. Regarding the defect acquisition, we use nanothermography. We really almost hadn't any defects, 2 different force with 122.64 microns on total area. And we perform, obviously, the fatigue tests. We use the norm ASM E8. This is the Baskin equation obtained and the fatigue limits for what we consider. Now, regarding the simulation proceeding, we first tested the Murakami model. So we first tested the universal values that he proposed. We assumed a fatigue limit of 4 multiplied by 10 power 5 because it was a convergence point. And we considered the total area of the defect for this analysis. And this was what we obtained. The model in red, the curve in red fitted better to the data. And this was just related to how the relationship between IE and IF was obtained. And it's kind of represented the logic, because if we admit a bigger defect, which it means that we are reducing the safety margin, and it means that we can apply a bigger stress to intended structure or intended component. So, although the results were reasonable, we tried to improve and propose a model specific for TE6L4V, gathering the data from nanothermography. We used the algorithm, again, Nelder-Mead and CLSKP. Those were the initial settings. We first introduced the settings of Nelder-Mead, which was really easy, although the SLSKP presented some challenge since the algorithm wasn't performing well. The algorithm was jumping for the boundaries. We couldn't find any convergence, and that's why we had to find a suitable initial guess to run the algorithm. As an optimization function, we use the negative R2 mean square, and those are the results. Well, both Nelder-Mead and SLSKP got to a similar solution. Therefore, we only consider one of the solutions. And it is interesting to see that the M stayed constant, which shows us that the slope of the curve wasn't changed during the optimization. And those were the results. Obviously, the curves were all overlaid in each other because we were giving, although we were giving different inputs, we were saying to the algorithm, go to the same solution, go to the same output. So we continued, and instead we changed the fitted curve. So the curve that we fitted with admissible area of defect of 1,000 of 2,000 microns, we changed for 1,000 microns, vice versa for the other curve. And of course, the results increased. Of course, we increased the error of the results, but we now have a curve which is more reliable and in terms of safety, and it's kind of slightly performed better for the model, for the curve fitted into the 2,000 microns, because when we give it the 1,000 microns defect area, it basically was assuming, okay, I can't be as I must be more conservative, and therefore the stress reduced and went to the left of the black curve. Now regarding the optimization process, Nelder-Mead, although it took more iterations, it was a safe algorithm to find a suitable solution, and SLSKP was jumping off, and it was kind of hard, as I explained, to optimize it. But it also got to a solution, although faster. And this is related to how the algorithms work. Nelder-Mead is an algorithm which uses simplex. It doesn't have information about the curves, which is trying to optimize, against the SLSKP, which is the gradient, the slope in each point. So as conclusions, we propose a prediction model that considers the intrinsic defects. we obtain a good fitting curve. So two models came from this work. As I've mentioned, the model fitted for 2000 microns was the most suitable, since it was the most conservative, and therefore it was better for real-world application. Now considering his algorithm, another MIDS is the most suitable algorithm for this type of methodology, since it's easier to set up, and since the computational power is not a critical factor with today's conclusion. And this research methodology, although it needs more deeper understanding, it suggests an approach to better quantify and qualify the manufactured parts, since we now are linking the defects with the SN curve, which it doesn't happen in the Baskin equation. And well, we are using as well the most advanced techniques for defects analysis. So those are reference, those are the authors, my contact email, the acknowledgements, and thank you very much for being here.